So, good afternoon, everyone. Moving to the third session of the day, it's my honor to introduce our guest speaker, Dr. Vaibhav Singhal from IIT Patna, who will be talking on strengthening of masonry using externally bonded cementitious matrix grid. Let me introduce you the speaker. Dr. Singhal is an associate professor and head of the Department of Civil and Environmental Engineering at IIT Patna. His research interests are in the design and behavior of structures under earthquake loads, experimental investigation, seismic rehabilitation, masonry structures, and seismic design codes. He has published 75 peer-reviewed papers in journals and conferences in the area of structural and earthquake engineering. He is a recipient of a prestigious Science, Engineering and Research Board International Research Experience Fellowship, that is SIRE, from Government of India. He received the Indian National Academy of Engineers very prestigious Innovative Projects Award for his doctoral research work. He was the founding coordinator of the Center of Earthquake Engineering Research at IIT Patna and a member of various committees involved in preparing design standards and guidelines. Recently, a design and construction guidelines for confined masonry structures drafted by him along with the other drafting group members have been accepted and published by the Bureau of Indian Standard. He has been actively involved in the training of construction engineers and structural engineers to build earthquake-resistant houses. Now I invite Dr. Singhal to please start the session. So over to you.
Okay. Thank you, Praveen, for such a detailed and nice introduction. I was not expecting that you will read out everything anyway.
It was really a pleasure for us.
So now the participants will be having a very high expectations, right? Okay. So first of all, good afternoon to everyone, and my best wishes for upcoming Diwali. We have already the vacations started here for Diwali celebration.
Okay.
Yeah. So I will be talking about, as Dr. Praveen has said, regarding the strengthening of masonry using externally bonded cementitious matrix. Now we all know, I think you might have seen in the previous presentations also, that the masonry somehow it has not performed well during the various earthquakes. And the reason we all know that it has a limited deformation capacity and also the limited tensile capacity. And if it is not reinforced, then definitely it can experience a huge damage during the earthquake. And there had been many examples. Recently, there was an earthquake also, I think last week in Nepal, where many structures also, especially of a masonry, got collapsed. And that shaking was so intense that we also felt the good shaking in Patna in this region also. Now, even some of the modern masonry materials which we use for the infill, like most of you have seen, are the participants are allowed to speak, or Dr. Praveen?
No, sir, not in between,
okay.
But they can ask the questions later.
Okay, no problem. So as you can see here, so like this is the most common, the masonry material which is now used as an infill material. So most of you will identify this as the AAC block, autoclave aerated blocks. And these autoclave aerated blocks also have a poor limited tensile and the compressive strength, and they also experience a lot of damages during the earthquake shaking. For the strengthening of masonry or for the strengthening of any structure, any civil engineering structures, so there are many techniques, but the techniques can be classified into two major groups. So one is we call as the epoxy based technique. So I'm talking about all externally bonded methods. So I'm not talking about the methods for improving the strength by grouting or some other methods. So I will be talking about the methods where we apply the strengthening technique over the surface by using some bonding agent. So the bonding agent can be epoxy based. We use various type of epoxies available in the market, and the bonding agent can also be a cementitious matrix. And this has been a new material or kind of a new area for research, which has been, I think, in last 10-15 years, a lot of work has been done, and many countries have also come up with the codes for strengthening using the cementitious matrix. Now, why the cementitious matrix have become popular in last 10 years? So the major problem which is seen with the, especially with the epoxy based, is, now this is an example of an epoxy based application. You can see here a fabric. A fabric can be of a carbon, it can be of a glass, or it can be of a different material, and it is applied over the masonry surface or any surface by using a bonding agent, which is a epoxy based bonding agent. So as I said, the major problem with the epoxy based is the requirement of a highly skilled manpower. A normal mason cannot handle the epoxy, and they cannot do a proper mixing and proper application. And also there can be some emission of toxic gases. And many times the epoxy, especially the low cost epoxy, they are vulnerable to fire also. And also you need to have a lot of preparation of the surface. The surface should be properly smoothened, properly cleaned before application of any bonding agent, which are epoxy based. So because of all these limitations, and that is how these cementitious matrix based techniques are becoming popular. And that is how the research has been going on in this area. So in this method, so what is done? So you can see here one of the picture where the fabric is applied over the surface, and then it is simply attached to the surface using a cementitious matrix. Cementitious matrix means it can be a cement mortar, or it can be any other type of a mortar, and directly pasted over the surface by using the cementitious matrix. Now there can be different application. There can be different methods which can be used. So let us say this is my masonry surface substrate. So we generally apply first layer of a plaster or first layer of a mortar, then put a fabric over it, and then apply another layer of a plaster or another layer of a mortar. So this is kind of a you can name it like a sandwich application. So where the fabric is sandwiched between two layer of mortar or two layer of plaster. You can even apply the fabric directly to the surface. So this is my surface substrate, masonry surface, and apply the fabric and then apply a plaster over it. So you can see here in this case, the bonding agent is my mortar or is the cementitious based bonding agent. So I'm not using any epoxy or any kind of other glue or bonding agent for attaching this reinforcement to the surface of the masonry or to the surface of a concrete. Now, the application of this is becoming popular in many countries. So you can see, especially in the European countries, they use this for the retrofitting of the vault, arches, even for the retrofitting of the masonry column also, it has been used quite popularly. And the courts also recommend the use of this kind of a system, which we called as the reinforced cementitious matrix for strengthening of masonry structures or even for the concrete structures also. Now this is one of the code. This code was developed from Italy, National Research Council, and these are the guidelines. So I'm just keeping a snapshot, and I know that some engineers and research scholars are there. If you are interested, you can go through this code and look at some of the guidelines, some of the design equations and design criteria which you can use for the designing of this reinforced cementitious matrix. Now the code suggests that it can be used for strengthening of masonry panels, walls, arches, can be used for the strengthening of floor and roof beams, and even for the confinement of masonry columns. Now, the challenge which lies in all this strengthening technique, of course, it is simpler to apply. Even mason who know the plastering work, who know how to do a plaster, how to put a mortar over the wall, can use or can take this strengthening technique and use it for improving the performance of masonry structures. But the major challenge lies in designing this, because the response of this material is more complicated as compared to the epoxy based. And that is where the researchers are coming into picture, and they are doing a lot of work to find out the properties of this reinforced cementitious matrix. So this is a typical behavior. If you test a reinforced cementitious matrix, I will show what are the tests can be done. So it will show typical such kind of a tensile response. So where the stage A is your uncracked stage, and then this is the stage where the cracks will develop. And then the stage C, there will be more number of multiple cracks, and the fabric or the reinforcing material will take some strength. And after this point, there can be a sudden or complete failure. Now, since this reinforced cementitious matrix, it will be attached to the substrate. Substrate can be a masonry or can be a concrete. Now the bonding between the matrix, or the bonding between the reinforced cementitious matrix and the substrate, will also play an important role in the designing of such a strengthening technique. Now, if suppose there is a failure, a bond failure, so in a design, someone has to consider that bond failure so that one can find out what could be the effective forces this reinforcing material can take. So there are some relationships, some tests which are suggested. We will see that how we can determine the effective design parameter for designing of these reinforced cementitious matrix. So coming on to the what are the different tests one can do. So definitely you need some advanced testing facility, or you can develop the facility in your labs. So the first test is you have to do the tensile coupon test. I will show what those tests are. And then you have to do some bond test. So bond test can be a shear bond, or somebody can do even the pull-off test also. So we will see what are these tests and how we can determine the properties. So now I'm going from the material characterization. Then we will see the performance of these strengthening technique on a small masonry specimen. And we will also see the performance of these strengthening material on strengthening of masonry walls also. So this is the first test, as I said, the tensile test, which can be done on the reinforced cementitious matrix. So this is a typical coupon or typical specimen you can see here. So here you can see this gray color, which is the cementitious matrix. Now, one can follow this code. This is the AC434, which was published in 2011. This can be used for the material characterization for the tension coupon. Let me give you some of the criteria or some of the suggestions which are given by the code. So it says that the shape of the specimen should be a rectangular, and the width should be at least equal to that, so that it can accommodate 3 strands. Okay, the 3 reinforcing wires or 3 fabric layers, and it should be more than at least 4 times the thickness of the specimen. The width should be kept as a multiple of a grid spacing, and the coupon length should be the grip distance plus twice the width plus the gauge length. And the longer the specimen, it is more preferred because the bending effect will be smaller. So this is a typical size of a coupon, the tensile coupon. So you can see this is the width, the thickness. So the total length will include the gripping area and will also include the area where you will measure the strain. And then there is some transition zone. So this is another picture from the test which we have done at IIT Patna. So here we have used the coupon of size 100 by 500. The reinforcement was also cut in that size. And then the first what we did, we have taken a 5 mm thick layer of a mortar, and then the reinforcement is placed over it, and then laid another layer of a 5 mm thick layer of a plaster, and then you can cure it for 28 days, and which can be later used for the testing purpose. Now this coupons or the failure under tension of the matrix can be classified into 3 different modes. The first mode, where you have a failure of the reinforcement or the failure of a matrix. In the second mode, there can be multiple cracks, and there will be a failure of your reinforcing material. It can be a fabric or it can be a wire mesh. Now another failure can be a bond failure, where the fabric or the fiber will simply slip inside the matrix, and there can be multiple cracks, and the failure ultimately can be because of the debonding of the fiber or reinforcing material from the matrix. Now these are some more pictures which were collected from the literature, that how these matrix, the cementitious matrix, reinforced cementitious matrix can fail. So you can see here, so here the failure is primarily the debonding or the failure of a matrix. Here you can see the failure, the rupture of the fabric, right? So there are different type of failures which can be seen during the testing. Now this is the failure which we have seen when we did the testing at IIT Patna. So you can see the multiple cracks which are seen in the coupon in the specimen, and using the peak load you can find out the ultimate strength of this, the cementitious matrix, the reinforced cementitious matrix. So here we have used the wire mesh, the steel wire mesh, and the strength was coming out to be nearly to the yield strength of the wire mesh, so which is about 403 MPa. Now this is how a typical stress strain curve you may obtain. So this is one idealized curve which we have obtained when we have tested the reinforced cementitious matrix, where the reinforcement is provided by using the glass fabric, and the cementitious matrix was simply a cement sand mortar of 1:4. So this is one test which can be used to identify or to find out the tensile properties of this reinforced cementitious matrix. Now the second test, which is also quite important, is to find out the bond, because we know that all these reinforcing methods or the reinforcing material is externally bonded to the surface. So it is important to know that how good they will bond with the substrate or with the surface. So there are various tests which you can find in literature, but till now there are no standards or the codal provisions available to do this shear bond test or a bond test for these externally bonded reinforced cementitious matrix. So few tests I am highlighting here, which you can find out in literature. So first test you can see here, this is called as a single lap shear bond test. And the last two tests are called as a double lap shear bond test. So in the first one, there is only the single brick, or you can see there are two surfaces of bonding. And in the second one, there are four surfaces of bonding. So this is called as first is called as a single prism and another is called as a double prism. So single shear lap or single lap shear bond test is quite easy. You can do it in the lab. You can develop a setup. So this is what the setup which we have developed at our lab to find out the bond strength. And the double shear or the double lap test can also be done, but the testing setups are more complicated and also it is more challenging. So we kind of adopted to go with the single lap shear bond test. So based on the literature, we developed our own setup. So from a literature, we find out quite a wide range of specification, wide range of specimens which they have used. So this is how you can see a typical single lap shear bond test look like, or the specimen look like. So you will have some bond length and there will be some unbonded length, and then you have some gripping length which is used for pulling it in the upward direction. So these are some of the pictures of the test setup you can see. So this is from another lab and this is from IIT Patna lab. And these are from all over the world, what they have adopted for this single lap shear bond test. And you can see in one of the lab, they have done also the double lap. So you can see here where the fabric is going in the forward direction and also in the backward direction. Okay, so coming to this more details. So the presentation file I will share, you can find out some of the more details that what dimensions we are adopted in our own lab, and which can be adopted, which can be modified to develop this single lap shear bond test. Now you can see here, earlier there were only 3 failure modes. Now in the bond test, you can have even more number of failure modes. Okay, so you can see the first failure mode where you can see that the bonding is very good and there is a failure of a substrate only. In the second case, you can see there is a failure from at the interaction between the substrate and the cementitious matrix. Another case, you can see the failure between the matrix and your reinforcing material, textile or fabric. And another failure mode, there can be a slip, there can be some mixed mode of failure also. And in the last case, you can have the rupture of the tensile rupture of the fabric or a textile or any reinforcing material. So that is what I want to say, that the behavior become more complicated when you look at the different properties. And the application wise, this is simpler, but the behavior wise is more complicated. Now here we have done the test with the steel wire mesh. So, and the failure which we have seen is the failure of the tensile rupture of the wire mesh before the debonding failure. So these are some more failure modes. As you can see, in the first case, we found the rupture of the fabric or rupture of the wire mesh. And in some cases, we found the failure of the in the cementitious matrix also. Now you can see here, there are a lot of failure in the cementitious matrix. And in this case, you can see a complete debonding. So when we use the low strength mortar for the strengthening purpose, so in both the cases, we have used the mud mortar, and mud mortar did not perform very well because of its earlier failure and also because of debonding from the surface. Now, using this test, you can find out that how much is the slip expected at the design forces, at the design level of force. So this is quite important test, which can give you an idea about the relationship between the bond stress and the slip. Now, if suppose you are unable to perform the bond test using the previous setup, so there is another popularly used method is the pull-off test. Now this pull-off test, you need some specific equipment. Generally the pull-off testers are available in various labs. So if you have this pull-off tester, so you can use also these pull-off test to find out that how much is the bond strength between the matrix and between the substrate, or between your reinforced cementitious matrix and the substrate. So this is a typical equipment you can see here. So what is done, that we used to cut a core inside the reinforced cementitious matrix and till some depth of the substrate, and then this is a disc which is attached to this core, and then this disc is pulled in the upward direction. And then we notice what are different failure modes, and at the strength at which this will fail, it will be divided by the total area. You will get the bond strength. Now here also you can have a different failure modes. So the first failure mode is in the substrate. If the failure is in the substrate, you can say that the bonding is good. There can be a failure between the cementitious matrix and the bonding and the substrate material. You can have a failure between the overlay, or between in the matrix itself. And then you can have also the failure between this the attachment and the surface. Now this is one of the failure mode which we have seen. I will show you some more failure modes. Yes. So you can see this is the test which is done on the reinforced cementitious matrix applied over the masonry surface. So we can have different failure mode A, B, and C. So first is in the substrate. So first failure mode we have observed in few specimens where the failure is seen from the substrate level. Then you can have the failure at the interface of your matrix reinforcing material and the substrate. So this is kind of a composite failure. And then you can have also the failure of the matrix. So this is the failure of the matrix. Now, all these results can be finally used to find out that how much will be the effective strain or the effective stress the reinforcing material or the reinforced cementitious matrix will take, my strengthening method will take. So what is suggested that using the bond strength test, so you find out also the effective or how much is the bond strain. And for that, take that bond strain and also the strain of your material, your reinforcing material, whether it is a steel or it is any fiber, carbon or glass. and then you find out what is the minimum, and this minimum strain should be also less than the strain which you have calculated from your tension coupon test. So using this, you can find out that how much is the effective strain my reinforcing material or my reinforced cementitious matrix can take. And this can be multiplied then by your modulus, and you can find out the effective stress in your reinforced cementitious matrix. So this is how, and that is why I have mentioned all these tests which can be used to find out that what could be the effective stress or effective forces which my strengthening method or strengthening layer will take. Okay, so these are some of the summary. So we have done a lot of tests in the lab, different type of reinforcing material, different type of cementitious matrix. So it is generally seen that if you use the larger amount of a reinforcement and your cementitious matrix is of a lower strength, then debonding will be the common failure mode. So it is suggested that you have to use appropriate size of reinforcement and also use the good strength of cementitious matrix. So something like you have to use at least 1:3 or 1:4 cement sand mortar for strengthening using this method. And by performing the various tests, test on the reinforcing material, tensile test on the coupon of the reinforced cementitious matrix, and the shear bond test, you can find out the effective strain, and ultimately you can find out the effective stress. So the design, you can see it is, you can think of like a design when you do a design of a reinforced concrete, any material. So where we find out, we see the yield strength of a material, we see how much is the bond strength, whether there is sufficient bond strength available or not. Accordingly, we provide the development length. So all these design concept will be also applicable for this reinforced cementitious matrix also. So you need to find out the bond strength, you need to find out the tensile strength, you need to find out the material strength to get the effective stresses which can be taken by this strengthening material. Okay. So just I will highlight some of the design equations. So again, so similarly, by performing all these tests, you can find out the limiting value of strain, and this limiting value of a strain will be further used to find out the design strength. Now the code suggests, so this is from CNRDT, from the Italian code. So it suggests different factors also. If suppose the material, the reinforced cementitious matrix is exposed to the surfaces, to the external environment or to the aggressive environment, it is suggested to use some factor of safeties also. So it is suggested for external application that you have to take this value of neta as 0.8. So this xd is the design strength or the design strain which can be used for further finding out the capacity. So this is the equation which is suggested by the Italian code. So where this VTF is the contribution of your reinforcing material, of your reinforced cementitious matrix. So it is equal to NF. NF is number of layers which you have, a number of reinforcement layers. TVF is your effective equivalent thickness. LF is the length. There are some modification factor, which is alpha. Now here, this is the important factor which we have discussed, finding out this epsilon FD. So this you have to find out by performing those tests. So this is your design strain, or you can say the effective strain which the material can take, the strengthening material can take. So these are some of the pictures showing the various components, what is mean by L, what is mean by H. So for giving the direction of load, so you have to choose the correct height, correct length. So the code also says that the total strength should not exceed the diagonal compression strength or diagonal crushing strength of your masonry. Otherwise, if you provide too much of a reinforcement or too much of a strengthening, it will not be very effective, because the masonry has a limited crushing strength and masonry can crush inside, whereas your strengthening scheme will be intact. So it is something like we try to avoid over-reinforced design in concrete. So similarly here also, we don't want to provide excessive amount of a strengthening, because the masonry will fail early before the failure of your strengthening material. So after finding out this VF, so VF is your contribution of a strengthening material, in this case reinforced cementitious matrix. You add this with the strength of your masonry and you can get the total strength of your masonry wall or any component, any member with reinforcing or strengthening material. Now to find out the strength of masonry, so there are different methods. So one of the method is you find out considering the minimum of different failure modes of masonry: failure because of sliding, because of diagonal tension, because of toe crushing, which is shown here. So these are common 3 failure modes for a masonry. So you have to find out the strength for each failure mode and take a minimum of that and find out the contribution of a masonry, add it to the contribution of your reinforcing method, and then you can find out the total strength of your wall, of your column, or any structural member. Now this is another code which is given by ACI. Recently there has been revision of this and they have done a lot of recommendations they have given how to design these externally bonded reinforced cementitious matrix. So I will not go into detail of this, and one important factor they have suggested is the effective strain. So instead of going into a lot of tests, so they directly suggest that effective strain can be taken as upper limit as 0.004. But this need to be some secondary thoughts are required for this, because from lot of tests and from literature, various data which are available, it is seen that this value seems to be quite low, and we will do a good amount of underestimation in the strength will be there if we consider this value of effective strain in the design. So the equation suggested by American code is quite easy compared to this Italian code. So where they have a very simple equation and they have suggested to use this FFV, which they call as effective stress, that how much the stress the reinforcing material or your reinforced cementitious matrix can take, and then multiply it with the length, area. N is your number of layers of reinforcing material, and 2 they have kept if it is applied on both sides. If it is not applied on both sides, you simply take it as 1. Now these are some of the photographs, application of these reinforced cementitious matrix. So in the first phase, what we have seen that how we can characterize the reinforced cementitious matrix. Now in the second phase, I will show you that how this reinforced cementitious matrix can help in improving the strength of the small masonry specimens. So what we did, one of the study I will just quickly go through, we did this on autoclave aerated concrete block masonry. So we have seen that AAC blocks or AAC masonry have also experienced a lot of damage. And we want to see that how this reinforced cementitious matrix can improve the performance of this AAC masonry. So we decided to perform a small or simple test, a flexure test, where the failure can be parallel to the bed joint. So you can see this is the failure mode. Flexure test where the failure can be perpendicular to the bed joint. So failure is expected something like this. And then another diagonal compression test to find out the shear or indirectly the tensile strength of a masonry. So we did some control specimens were there where no strengthening was used, and there were 2 type of a strengthening technique we have adopted. So first one is having anchors. So where the fabric is also, you can say, to avoid the debonding, the fabric has been attached to the surface also by using anchors. And in the next case, we have used adhesive mortar, thinking that it will provide a better bonding. So adhesive mortar is nothing but the mortar which we commonly used for laying the AAC block. So you might have seen this adhesive mortar which are given by various companies like Ultratrack and other companies. And sometimes they call it as a polymer mortar also. And for each case, we have five specimens. So this is the fabric which we have used. So this was the main fabric which we have used, having a grid spacing of 25. And this fabric we have placed at the edges because we want the anchors to be easily placed. So for easy placing of anchors, we have used this fabric at the edges, which is having a small grid spacing of approximately 8 and 10 mm. So as I said, two type of techniques we have used here. So in the first case, what we have done, so we have applied first the layer of a adhesive mortar, the polymer mortar, and then simply put a fabric over it, and then put another layer of a simple cement mortar. And in the next case, the second technique, which I'm calling as an anchor technique, so in which the fabric is directly placed over the surface, and then we install the anchors at few locations and then covered it with the plaster. I think I have some actual pictures I will show you, and these are some tests which were done on AAC masonry. So this is the compressive strength of a AAC masonry. We found out as 1.8, and the tensile strength is 0.13 MPa. Some bond tests were also done for different strengthening technique. It comes out to be approximately 0.41 MPa. So these are the tensile tests. Again, so tensile tests were done on both type of on two type of strengthening techniques. So where the fabric is embedded inside the cement mortar so it is kind of a sandwich between both cement mortar, and in one case it is sandwich between one side it is adhesive mortar, one side it is a cement mortar. We found out nearly the similar properties for both the cases, so there was not significant difference between the adhesive mortar and the cement mortar. Yes, so this is what I was talking about. So this is called as the anchor technique. So you can see this is a plain surface of a masonry. So we first applied the main fabric. Over the main fabric, we have this edge fabric, and then these are the anchors. And anchors are the simple anchors. You can use simple your nut washer assembly also to use them as an anchor. And then directly applied a thick layer of a mortar, 15 mm. And whereas in the another technique, what we did, so this is your masonry surface, then we applied the fabric. We kept the edge fabric also to just to have a similarity with the anchor fabric, and then applied the polymer mortar, the adhesive mortar, so that the fabric should be properly adhere to the surface. And then after drying, we applied the 10 mm thick cement mortar. So these were two techniques. These are test setups. So this is for the flexure test. This is for the diagonal compression test to find out the shear strength. And these are the responses of the flexure test. So this is first one is for the control specimen. There were no strengthening. So it was expected that the control specimen, which is not strengthened, will be having a very low capacity, and compared to the control one. So both the strengthening techniques, so AN is for anchor and AM is for the adhesive mortar. So both were good. So both have given nearly the same improvement in the flexure strength, and also they both of them give the same improvement in the flexure strength perpendicular and flexure strength parallel. So these are some of the failure pattern which we have seen. Now, in some cases, especially when the anchors were not used, we have seen the debonding, and which is not preferred. So even the adhesive mortar, of course, it is having a good adhesive property, but the debonding were commonly seen, especially without anchor. So it is suggested that some anchor should also be used when we are using this strengthening technique. Now, these are the results for the diagonal compression test. So again, the diagonal compression test also showed quite similar results for both techniques, for anchor and for the adhesive mortar. And this is how the failure has been seen. So again, with the adhesive mortar, as you can see at the bottom, there was a debonding observed. Now, the control specimen failed suddenly. So there were complete disintegration of the specimen when we tested without any strengthening. Now, this is a comparison of the strengthening technique. So you can see here, so D is the anchored one where we have applied directly, and A is your adhesive mortar. So both you can see, so both this bars looks almost of a similar height. So both of them give us a comparable results. Only the problem with the adhesive mortar or without anchor, we have seen that there can be a debonding at different places. So all these results have been already published. So those, if you are interested, you can go through in detail. So now coming from the small test to the major test on the walls. So here what we tried, we tried to improve the performance of the masonry infills. So masonry infill used in the reinforced concrete frame. We have seen that during the earthquake that the masonry will completely fall out from the frame because of the poor bonding and because of its poor tensile strength. So this study was done in IIT Kanpur. So when I was working as a postdoc in IIT Kanpur, so where we did the testing of 6 half-scale masonry walls, reinforced concrete reinforced concrete frame with masonry infill. So all were of a half scale, and these RC frame were simply designed as an ordinary moment resting frame. So they are not designed as a spatial moment resting frame. So we choose the FRCM, the fabric reinforced cementitious matrix, for the strengthening of these walls, masonry infill walls. Now here also we have chosen 2 different techniques. So first was the sandwich one. So where the fabric is sandwiched between the 2 layer of plaster. So first layer of a plaster was 2 mm. Then we applied the fabric, and another layer of a plaster was 4 mm. And in the direct method, we have directly applied the fabric over the surface and then put it a plaster of 6 mm, total thickness of. So total cementitious matrix thickness was 6 mm throughout for all the specimens. Now in this also we have tried with anchor also. So both technique have anchors and without anchors. So let me show you the test matrix. Yes, so this is a test matrix. So total there were 6 specimens. First was the control. There were no strengthening, but it have a plaster also, a plaster or mortar. Then second one is your sandwich mortar, no anchors. Then the direct one with no anchors. Then again the sandwich with anchors and the direct with anchors. And then we tried another one where the fabric is placed at an angle of 45 degree. In all other 4 specimens from 2 to 5, the fabric were placed at the 0 and 90 degree orientation. So yes, this is the fabric which we have used. So again, so this was the main fabric and this is the edge fabric. So edge fabric was primarily used to make the application of anchors much easier. So you can see the placement of anchors. So anchors were designed in such a way that the anchor should not fail before the failure of a fabric. So the shear strength of these anchors were kept more than the tensile strength of these the reinforcing material. Property wise, both fabrics were having nearly same material properties, say same tensile strength and same properties. Only the spacings are slightly different. You can see here the main fabric is having a spacing of 25 mm and the edge fabric was having a spacing of approximately 8 mm. These are the properties of masonry. Masonry mortar was having a strength of 8 MPa. The compressive strength of masonry we also got at around 8 MPa. The strength of a plaster or the mortar which is used for a plaster was 15 MPa. These are the properties of a concrete, and these are properties of a reinforcing steel used for the construction of a reinforced concrete frame. Now this is the test setup. So here in this case, we have used a very unique test setup. So where the specimens are subjected to a sequence of in-plane and out-of-plane loads. So the objective here was to see the performance of a masonry wall when it is damaged. And especially if any damaged wall is subjected to out-of-plane shaking, it is more vulnerable to a complete failure. So that is what the objective was, that we will put some damage to the wall and then do a shake table test and see how it will perform. So that is what we have done. So this is the sequence of our testing. So this was the loading protocol. So first we did the out of plane loading. The wall was shaken in the out of plane direction. So we did without any damage. So just to see whether the wall is stable without any damage or not. And we applied the ground motion in the increasing level of shaking. So So you can say that first of all applied for zone 1, zone 2, zone 3, zone 4, and zone 5, like the zoning system we have in our India. Of course, there is no zone 1, but we started with zone 1, 2, 3, 4, and 5. And then after that, we recorded all the displacement, accelerations, and other responses. And then we applied some in-plane load. Okay, we applied the in-plane load till we observed some cracks, some damage. And then again, we applied the out-of-plane loading and continued the sequence of in-plane load, then again out-of-plane load till the complete failure. This will be more visible. I think, let me show you this video, then it will be clear. So this is the video of a control specimen. There is no strengthening, but it has, the wall has been plastered and everything has been done. Okay, so first you have seen the out of plane shaking. You can see the wall was kept over the shake table. It was shaking. Now in plane damage, you can see there are some damages, some cracks, and then again the out of plane shaking. I hope the video is visible to you. Maybe because of internet, some of you may not see it in a real. So you can see there are a lot of damages in the wall, and you will also see that the wall has been completely detached. So if you will clearly observe that only the frame is deflecting, the wall is not deflecting, and the some portion of a wall has also fallen during the out of plane shaking. So in the next cycle, you will see the wall has been almost kind of a dismantle, or it has been coming outward. Now, because of these, some of the restraint, because of the out of plane support, the complete failure we have not seen, but the wall was almost kind of on a verge of a complete collapse, out of plane collapse. So this is a response of a control specimen. So in the control specimen, so this is in the first curve shows you the in plane response, and the second curve shows you the out of plane displacement response. So we have seen a large amount of out of plane displacement with the in plane damage. So you can see that the displacement was going more than 10 mm. And even for a higher cycle, I have not plotted here, but the displacement was quite high. It was even more than 30-40 mm. And if you will see, so here, this S letter shows the separation of a masonry from the frame. So we have seen a very early separation, even at a very small drift, the masonry has been separated. Yes. Okay. So this is a response of a wall with no strengthening. Now this is the next one. So this is a response of a wall which is strengthened by using the sandwich technique. So sandwich technique where the fabric is sandwiched between the two layer of a mortar. And this is for an unanchored case. So there are no anchors used. So let me play this. So the response was better than the control specimen, but what we have seen that because of presence of no anchors, or because when there are no anchors, so we have seen that there was an early separation of a wall from the RC frame, from the reinforced concrete frame. Now you will see here, if you will look at the bottom corner, during the in-plane loading, the plaster is completely plastered with the masonry is simply moving, and the frame is, so you can see there is a lot of slip of the, or you can see the debonding of a plaster. So here is the response. So again, what we have seen here, that again for this wall, when the fabric was not anchored, so there was large out of plane displacement again to the amplitude of 15 mm, especially at the bottom part, because the bottom part was completely debonded. And the separation was also seen quite early. You can see the separation by the letter S. The separation was again near to about 0.5, 0.75% drift. There was some improvement in the strength, but no significant improvement. but the problem was that the strength after reaching the peak have reduced suddenly, and also there was an early separation from the frame. The specimen with the direct application, even if it was unanchored, have shown the better performance. You will see the separation was delayed. You can see here the S was at a later stage, and also the drop in the strength after reaching the peak was much gradual compared to the previous one. And also it has been seen here that the out of plane response was more uniform, and we could not see any significantly large out of plane displacement as compared to the other unanchored scheme. Now these are the responses for the anchored one when we have using the anchors to attach the fabric to the surface of the masonry or to the surface of the frame. So definitely, as expected, this has performed better, especially if you see the out of plane displacements. They have been always, even with the extensive damage, it was always less than 10 mm, close to 5 mm. And also the separation was not seen. You cannot see a separation here. So there was no letter S here in this curve. SS is different. SS stands for the shear crack in the column. So no separation of a masonry from the reinforced concrete frame was seen if you will do a anchoring. Yes, so this is a video for the anchored one. Now you will see a better response of an anchored one, and you will not see the separation of a masonry from the surface. And the cracks were also more uniformly distributed in this specimen compared to the previous one. So under the out of plane response, there was no damage, no excessive deformation. And you will see the first time you are seeing there is a horizontal crack. So this is all happening because the masonry is also contributing. The masonry is also taking good amount of forces, and it is also participating in taking the in-plane forces. Okay. Yes. So this is the response for the direct anchored. So direct anchors and the sandwich anchored, they have performed almost nearly same. Again, for the direct anchored also, we could not see any separation of a wall from the frame, from the RC frame. And the out of plane displacements were also significantly lesser compared to the unanchored or compared to the control specimen. And this is a response of a specimen which is having the fabric at an angle of 45 degree. So this specimen gives us the maximum strength because generally the tendency always you will see when the masonry is present in the RC frame that loads are transferred primarily through a diagonal. So when the loads are transferred diagonally, so definitely the oblique angle or the 45 degree angle placement of a fabric will take better forces, or you can say the distribution of forces will be better in the fabric, and that is why they have taken the maximum strength. But what we have seen that because they are taking the maximum forces, the fabric, so we have seen the early rupture of the fabric, and because of which at some places we have seen some large out of plane displacement because of those early failure of a fabric during the in-plane cycle. So if you want to compare the failure pattern, so for the control specimen, as you can see, some part of a masonry was completely failed. It was coming outward. Now this is a response for the unanchored for the sandwich technique. So you can see there was no damage in the masonry wall. So most of the damages were seen in the frame and at the interface of frame and the wall. Similarly, for the direct unanchored has performed slightly better than the sandwich unanchored, but again, the masonry was having minimum damages. Most of the damages were concentrated on at the corners or at the interface of masonry and the RC frame. Both the anchored specimens have given a better performance, better distribution of cracks or failure in the wall and in also in the frame. And similarly for the anchored one, which is where the fabric is at 45 degree, also have shown the better response. So these are the comparison of all the specimens. The strength improvement is not so significant, but the most of the improvement what we have seen is in the out of plane response. So the out of plane displacement have been much lower when you will apply the adequate strengthening, and especially with the anchors. So finally, what we have find out from these tests of the masonry infill with RC frame, masonry infill in RC frame, that if you will apply this strength technique, so definitely your frame with masonry infill will provide a better response. It will maintain the structural integrity and the better ductile behavior. Direct application, we have seen it has shown better performance compared to the sandwich one. And of course, the mechanical anchors are helpful. Mechanical anchors avoid the early separation of a wall from the frame, and it improves the efficiency of the FRCM. The oblique orientation was effective in increasing the strength, but it was not as effective compared to the orthogonal orientation because it lead to the overstressing of fabric, and because of which we have seen that there can be a large out of plane deformations. Now, the final concluding remarks are that this type of a strengthening technique, the reinforced cementitious matrix, is quite promising. It is easy to implement, but we need to do a lot of work, especially to find out that what could be the acceptance criteria for designing of these reinforced cementitious matrix. Acceptance criteria in terms of the effective strain, the effective stress they can take, because the effective stress or effective strain will depend on the interaction of the reinforcing material within the cementitious matrix, and also the interaction of this reinforced cementitious matrix with the substrate. So it is important to perform some of the tests to find out the property, and one can also do some small tests to see or to evaluate how these strengthening technique should improve or will improve the performance of masonry or any other structural component. And then finally, if the facilities are available, of course, you can do test on the masonry walls or other components to see the level of improvement or to understand the behavior of these strengthening techniques. So I will stop here. I think I am almost on time. So if there are any question, any discussion, I will be more than happy to answer.
Thank you. Thank you so much, Dr. Singhal, for such an enlightening session. You have included a very comprehensive explanation describing the behavior of cementitious matrix composites, the insights on the application techniques of such composites to masonry substrates, and also covering the full-scale test showing the seismic performance of masonry infills with and without FRCM composites. So we are really fortunate that you have covered and given a overview and also a full spectrum about from the material characterization to the structural level testing and its behavior in detail. So we have few questions for you. The first question is related to the direct application and sandwich application, which you have talked about.
Yes.
Is there any specific difference in behavior or in strength performance when we are applying the direct application method and sandwich application method? You talked about that in one of the technique, there will be a debonding failure, which is significant. Apart from that, is there any specific observations?
Yes. So like in one of the technique which I have shown that there was a debonding. So one thing you should notice or keep in mind that in that technique, we have not used the anchors. And because of those anchors, there was a debonding. But even in with the sandwich technique, if you use the anchor, so their performance can also be a better performance. So our intent was to compare the direct or sandwich was, the problem with the sandwich technique was that when you apply the first layer of a plaster, then you have to apply a fabric. Then the second layer of a plaster, you have to do within a minimum gap, because if the first layer will get set, then there can be again a debonding between those two layers.
Right.
So from the application point of view, that is what we want to explore, that can direct will be similarly equivalent to a sandwich one, or it is inferior, or it is better. So what we have found out from all these tests, that direct was almost equal, or in some cases we have also seen that it is slightly better, because the mason which is applying or using this direct or sandwich application, the masons are more comfortable in the direct one compared to the sandwich application.
Okay.
So you can say that the quality control or the whatever you can say the precision which you want to achieve during preparation of a specimen was better in sandwich, in the direct application compared to a sandwich. So I will say that the results point of view, the variation in the results were lesser in the direct one compared to the sandwich application. And so that is what we suggest, that the direct can also be used depending upon the convenience at the site.
So there is a follow-up point. Let us consider a situation where the kind of reinforcement which you are using for FRCM composite is with a very, very small grid spacing, right?
Right.
In that case, the direct application will work.
No, in that, see, direct and sandwich application are independent of that. Okay. Now, the problem is that if suppose you are having a very small spacing, okay, even if you use the direct or even if you use the sandwich application,
Sandwich.
so the problem will be there will be always a chance of a debonding if the grid spacing is small. Now,
Right.
if the grid spacing is small, the chances of debonding will be higher in the direct application compared to the sandwich application. So what will happen, that if you use a direct application and with the small grid spacing, the debonding can be between the substrate and the matrix. Now, in the sandwich application, the debonding can be between the matrix itself, between the two layers of a matrix, if the grid spacing is smaller. And there have been a lot of research. They always suggest that you should have a sufficient grid spacing if you want to use this technique and without anchors. If you are using the anchors, then even the small grid spacing can be used.
Will hardly make. So you mean to say that indirectly, if the anchors are used and if we do not want the debonding to happen, it indirectly means that we want the tensile strength of that composite or the reinforcement to be fully utilized in order to have a better performance.
Yes.
Okay.
But if you use the adequate grid spacing, even the anchors are not required.
Adequate grid spacing, you mean?
Adequate grid spacing, that the spacing should be such that the masonry and the matrix should have a good interaction.
Okay. The better interlocking.
Better interlocking should be there. Like what we have seen, like 1 inch spacing is quite good enough. In that case, the debonding is not generally seen.
Okay. In one of the slides, you talked about this idealized stress strain curve, right?
Yes.
And there, I just saw the value in the y-axis where the stress seems to be very less. It is in the order of 1 to 2 MPa. So I was keen to know.
I was expecting a question on that. So actually, in that graph, the stress was calculated by considering the
Using mortar area?
Total area, yes.
Total area.
Okay. So I think that intention was because we want to use that property from our finite element analysis, where we were trying to model it like a complete composite, not the separate layer. But actual the strength, you have to divide it by only with the reinforcing material area. Yes.
So my next follow-up questions is that we have observed in many studies, the researchers represent the tensile strength of a reinforcement or for a composite, mostly in terms of force per unit length, either in terms of mortar area or either in terms of force per unit length, where they divide simply force by the grid spacing. Suppose I have two conditions. You talked about the wire mesh. Wire mesh is very rigid. It has a specific cross section. You can calculate by using vernier caliper or some kind of a tool. And then you know the shape of the cross section. And then you can calculate the area very easily.
Right.
But in case of a fiber reinforced reinforcements, what exactly happening is that this material is very flexible in nature, right? So how to calculate the area so that we can represent the results in terms of stress? Is there any specific technique or methodology one need to adopt?
No, no, no. So that is what like challenge also we are facing with the fabric when we use the
Mm,
fabric. So what we do that uh, we are not actually using the pre-treated fabrics. Okay, or you can say we are not using kind of any virgin fabric. So what
okay,
we are using the pre-treated fabric. So where whenever the fabric which we are receiving, we are receiving in the form of a grid.
right, right.
And the grid, when you have this fabric, the pre-treated fabric in the form of grid, so it is much easier to find out the area of the one element of those grids. And then we
Strand,
use,
okay.
yeah, that is
Mm,
strand or what. And then we use
mm,
that like in a similar to the wire mesh. Of course, the challenge is that if suppose you're making your own grid or own textile fabric, so you have
mm,
to then find out the volume of a fabric and then the volume of a whatever the epoxy which you use for the impregnation, and then things will become slightly more complicated. Of course,
more
the
complicated.
guidelines are not there.
Mm. Because sometimes in the literature, we see that people quote the tensile strength of a composite, let's say 2000 MPa,
Oh, yes.
2500 MPa.
Yes.
But in reality, when we test, let's say if the load at which it basically fails or ruptures, let's say 4 kilonewtons. Now, the main challenge, as you have correctly pointed out, that how to calculate this area. And because of that, we are not getting a true picture that how
Mhm.
much exact stress that particular composite is capable of and what the designer has to use, especially in case of an analytical modeling or even at the time of prediction. So there is a large difference between these two. So people say that it's a 40 kilonewton per meter strength, 50 kilonewton per meter strength sometimes. So that's why I'm asking this.
Right, right. So those are some challenges, and many times you will not get full properties available in those papers also.
Yes,
Mm.
yes. Uh, Sir, is there any specific guideline which talks about that how much or what is the maximum amount of reinforcement one need to provide, especially with respect to FRCM composites? Because we do not want the masonry to fail in crushing, right? In case of an over reinforced section. So is there any specific guideline which talks
No,
about the
the
maximum
guideline is
reinforcement?
not there, but I have highlighted some of the equation which are given by the Italian code. So where what
Okay,
they say that you find out the total strength of, let us say you are strengthening a masonry panel, total strength of a masonry panel with masonry plus strengthening contribution, and that total strength of a masonry panel, it should not be more than the diagonal crushing strength of the masonry.
okay,
Okay.
okay, okay.
So that is how you can check that you are not providing or one is not providing excessive reinforcement or excessive strengthening reinforcement
Hmm.
for the masonry panel or for any component. But as
Okay,
such, there are no guideline or criteria like we used to have for a designing of a reinforced concrete member, where we
right,
have
right.
clear criteria like over
Hmm.
reinforced or under reinforced criteria. So those
Hmm.
guidelines we do not have in our course.
Because in the literature, people have used, let's say, in case of a small masonry wallet, one layer of a mesh, followed by double layer of a mesh, and they have started. And somewhere they feel that no, this is the optimum reinforcement one which need to go for. But component level testing is far different compared to the main structural level testing, right? So what should be because the grid spacing is directly related to the area of reinforcement. If you're
Right.
increasing the grid spacing, the area of reinforcement is going to reduce. The another question is, can we use this FRCM system as a strengthening measure for or retrofitting for historical masonry? What's your take on that?
Yeah, definitely. Definitely. Even we have in Bihar, we have used this for some of the projects also. So the good thing is
Okay,
that because since this is a cementitious matrix, so cementitious matrix can be, you can play with the different kind of bonding material. So like in one of the application, we have used the lime mortar. Okay. Now the problem only which is there, if suppose, because any strengthening intervention which you are doing on the historical masonry, those mortars should be compatible with the historical mortars also. Okay.
Okay.
Now all the historical mortar which you will find that they are primarily either of a lime or they will be of a mud. Now the problem with these lime mortar or mud mortars are that their strength is quite low, especially in the earlier days.
Okay.
Okay. And we have also done, I have shown some results for the mud mortar also, and those are also published. Even for the lime mortar we have done. So problem is that especially with this low strength cementitious matrix, the bonding failure is much more prominent. So they will be more vulnerable to the bonding failure, especially in the early age. We have not done still the testing on the higher ages or long ages because of the limited
Okay.
time. But definitely
Yes.
with the age, when they gain their strength, so they will perform better. But in the early ages, since they have a limited strength, we have seen the early debonding of these materials. But they can be used definitely.
Uh, Mr. Sri Bhanu Pratap is asking, his statement was, I'm wondering what are the reinforcement types, that is fabrics, that can be attempted for retrofitting. I mean, he mean to say different materials related to FRCM composite. You said carbon, glass, basalt.
Yeah. So see, depending upon the availability, any type of a material can be used.
Right.
In India, fabrics are not easily available.
Available.
In
So,
some places, it is now available. Many companies are importing them from outside. Most commonly, which is available is the carbon fabric. Glass fabrics are also very rarely available. So what we suggest that if you are using the high strength fabric, let us say carbon, so you cannot use the normal strength mortar like mud mortar or cement mortar 1:4 mortar. So in those cases, you have to go with the special repair mortar. So where it
okay.
is expected that you should have at least a strength of 40 MPa.
40, 40.
Yes, yes, yes.
Okay.
Otherwise, these high strength fabric, they will not very effective, and they will simply debond, or they will break the matrix and they will debond.
Okay. It
Okay,
means the tensile rupture of the reinforcement will not happen
will not
in such
happen
a case.
if we are using the low strength mortar.
Because in one of the American guidelines I was reading, they typically said a mortar has to be in a range of around 18 MPa to around 30 MPa, something like that.
No, no,
So
no.
even in
American code simply says that should be at least 40 MPa.
40. Okay.
Mhm.
Okay.
They don't recognize these low strength mortar.
But in India, as you have in one of the
Mm.
slides, you have pointed out that we have to minimum use 1:4 or 1:3.
Three.
But
Yes.
still, in Indian context, even if we go for OPC of 53 grade, or even with a PPC with a good quality of sand, it is very difficult to achieve with 1:4 or 1:3 more than 20 MPa.
That is true. So that is what, if you are using this low strength mortar, or I will not say low, but medium strength. So either you can go with the wire mesh or you can go with the glass fabric, but
Okay.
do not go with the carbon fabric with these low strength
You
mortar.
mean especially with respect to high strength composite, one has to
Yes,
use the special type of a mortar,
yes,
which is
yes.
having a very high compressive strength.
Correct,
Okay.
correct.
There is another follow-up question of the same participant. Does the modular ratio play a role here in the choice?
Modular ratio, see, definitely modular ratio will play a choice, but the problem is that many times you do not have a control over these things. Okay. We also talk about modular ratio in the design of reinforced concrete and other things.
I see.
We see the compatibility of concrete with the steel. We assume that the strain will be the same level and all these things, right? So those are all assumptions we can take. But as I again said that if you are having a low strength mortar, so always go with the low modulus and the low strength reinforcing material. Okay.
Okay.
what drives the
So,
choice of mud mortar made in the investigation?
made in this
So
investigation.
like, as I think I have already answered, as Dr. Praveen asked, that a strengthening of a historical masonry. So we want to see that if suppose, because most of the historical masonry here in I think around the world, they use mud mortar or lime mortar. So we want to see that if suppose those buildings has to be, or historical monument has to be strengthened, so you have to use a compatible mortar. So compatible mortar will be having the same constituents compared to the historical one. So that is what we tried. We tried to see that can we use the mud mortar or a very low strength mortar for
Right.
these strengthening techniques also. So the response was not good, not very promising. So mud mortar performance was not good with the,
Poor.
even with
Hmm.
the wire mesh, with the low strength material.
Right. Right. Okay. And one of the participant is asking in slide number 9, you showed a picture of strengthening of RC column. Can you explain that?
Achha, those I
He's,
feel is
I feel
spike anchors.
spike anchors are used in that
So you are correct. So
special type of
those are called as the anchors which are prepared using the same fabric. So we are not
same fabric.
we do not use the steel anchors or some other kind of anchors. So you can search in a literature which are called as a fan type anchors. So you will get a lot of literature on that.
I think it is also very much common, and current research is also going on, especially in the context of FRP composites, where these fan type anchors are very used in order to prevent debonding failure there.
Yes, yes, yes. The good
And
thing is with a
his
fan
follow-up,
type, good thing with the fan type anchor is that you can simply flatten them and they will give a good finish. With the steel anchors is that they will coming outside and you have to cut those steel anchors, and then plastering over the steel anchors always create a problem. So fan type anchors is that you can get a good flat finish surface after
hmm,
using these fan type anchors.
okay. So for using these fan type anchors, uh, do the drilling has to be done prior to the application of FRP composites?
Yes,
Because you have to
so
wear
that is
two
what,
holes.
so that is what like another challenge, especially with the sandwich method is. So that is
Uh,
what like you will see that why we are preferring direct application. So direct
yes.
application has an advantage. So you drill, you
Hmm,
put a fabric, you put your anchor, and then simply flatten it, and then use cementitious matrix to keep it intact. And then you apply
right.
one layer of plaster. With sandwich one, you have a challenge, because with
Right.
the
Right.
sandwich one you have to keep that hole, because hole can be drilled only
Intact.
prior,
Hmm.
right? You have to keep
Right.
that hole
Right.
intact so that the plaster should not go inside, then put a
Hmm.
fabric, so things become little more cumbersome with the sandwich method. Then there was a question regarding the fiber mesh. I think that is already answered.
He in the last point he said slide 21 how you have calculated the area of glass fabric to calculate stress.
That is what I already told. So we had a
Pre-treated.
pre-treated and which was having the definite size of the grids. So we
So
use the
it's like a rectangle width
rectangle,
into
so
thickness
yes, we use the screw gauge and the vernier caliper to find out the
screw gauge.
size of, yes.
Oh,
So prefer always use the screw gauge when you are measuring anything which is less than 1 mm.
okay. Even some nowadays this digital vernier caliper is coming. Will it be preferable or only screw gauge
It
is
it is preferable, but problem with the even with the digital vernier caliper, when things are less than 1 mm. So if you will measure, let us say, do a measurement of the same material or same location couple of times, you will get good
right?
differences, because the initial there can be some kind of a backlash error or some kind of a lack or misfit can be there.
Okay.
So less than 1 mm, you will not get a good accuracy with vernier.
Okay.
The screw gauge is easily available. You can go to any mechanical
Yes.
workshop, mechanical labs. It is
And
there.
even it is very cheap. Uh, 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 Last second question, it is out of curiosity I'm asking. Let's say when you are talking about the fiber mesh, there is a strand, right? This fiber strand consists of multiple number of fiber yarns.
Yes.
When the manufacturer say the mechanical properties or the description about the composites, whether that strength is of a yarn, I mean a filament of a fiber yarn or of a particular strand, because the cross
It
section of the yarn is in microns, right?
Mhm. So they will generally give, the manufacturer will generally give the strength of your yarn, one fiber.
Yeah.
Single. Yes, yes. You can
So I
ask
think
them,
that, yeah,
they can provide the strength of a strand also.
okay. Because I think that may be the reason why the strength seems to be very high, 1500 mpm. Because when you calculate for a strand, the strength never comes out to be so high.
And strand also
That is
have
our experience.
the strand also have some good portion of epoxy, another thing which is used for the
Yes,
impregnation purpose.
impregnation purpose.
So whatever the strength which they report is there is for only the single fabric.
Okay.
So
So the
like
last
carbon,
question of the day, yes, sorry.
so carbon, like you will get something around, always they will mention about 1000 or 1500, and for the glass
Mm,
they will always mention about 600 or 700 MPa.
right, right, right. My last question is related to in-plane failure patterns.
Mm-hmm.
As we know that this in-plane failure pattern depends on two main factors. One is the pre-compression load or the gravity load which is coming onto the wall, and second is the aspect ratio,
Correct.
because of which the different in-plane failure patterns occurs, maybe shear, in-plane shear or in-plane bending. Do we have any quantified parametric ratio which states that at this axial ratio or at this aspect ratio, this type of failure usually occurs? Because in the literature, the statements are written in a very qualitative manner. If it is low, if it is high, then this type of failure occurs. So I just want you to comment on that. Is there any specific ratios are related to it?
No, actually, no such ratios are available. So, because it will also depend upon your type of masonry and other parameters also. So, what many researchers have done, they do not mention it, the relation with the axial compression. So they say that the ratio, what they do, they take a ratio of axial load divided by the masonry strength. Okay, so
Okay,
something kind of
okay,
a, and what you can do, and even some of the students can also try that, even from the basic principle of your mechanics also, so you can try to develop uh, these ratios also. You can try to develop the curve which define
okay.
like flexure, considering only the flexure mode of failure and considering
Only
only the shear mode
shear,
of failure. And then
right.
when you will plot them with the change in
Hmm.
the axial compression, so you will get some intersection points.
Intersection points,
Yes.
right,
So
right.
a lot of work has been done. You can see some papers by Professor Guido Magnus. So he has done some work on
Hydromagnets.
stone
Okay.
masonry also. So where he has given such kind of a curves that you can find out those critical boundaries where the failure will be governed by the shear or the failure will be governed by the flexure depending upon the amount of axial compression. But
Okay.
those will be only valid for a given masonry and given strength of masonry. So that is why all these codes are not giving any specific limit, because it
Limit.
depends upon the material strength also.
Okay. Okay. So I think we have answered all the things. Yes. My last question to you, since you said stone masonry, since the density of the stone masonry is comparatively very high compared to that of brick, do you think that this kind of a FRCM strengthening system will play a great role in enhancing the stone masonry performance as a retrofitting measure?
See, the major limitation with all the externally bonded strengthening methods, whether you take FRP or you take FRCM or anything,
FRCM.
so they will not contribute significantly in the strength. If you are expecting an improvement in the strength, so those contribution will be very small. It will not go more than 20%, 25%. If you have to go
Okay.
beyond that, then you have to use lot of fabric and very high strength mortar, which will
Mortar.
again will become very uneconomical. So
Right.
what is the good or advantage with all these methods is that they will help in improving the tensile strength and help in maintaining the structural integrity. Okay.
Okay.
And
Okay.
ultimately the deformation capacity or ductility
Large deformation.
will improve. But
Okay.
strength improvement will not be significantly high.
Significant. Okay.
Yes. So the same reason, like to answer your query to the stone masonry, Of course, it can be used, but it will only help in maintaining the structural integrity, in improving the deformation capacity, not the strength.
So you mean to say, in achieving the integral box action, one can easily go for these type of
Yes,
composite materials.
yes,
Okay,
yes.
okay. Thank you. I believe that the questions of all the participants have been answered. And if there are any further queries, one can reach out to Dr. Vaibhav Singhal through an email. And depending upon his schedule, he may like to answer some of your questions if there is any. And finally, as a mark of respect to Dr. Singhal for the time and valuable input he has shared with us all today, we would like to offer an e-memento as an effort of appreciation.
Yes.
I I call Lakshmi to please share the e-memento with Sir. Sir, on behalf of everyone, we would like to thank you. Your presence has been valuable to us today, and we certainly look forward to another interesting interaction in the near future. Thank you so
Sure,
much, Dr. Singhal.
sure,
Thank you
sure.
so much.
Thank you. Thank you so much for this digital movement, and thank you for inviting. And I hope
Pleasure, sir.
all
Pleasure.
participants have a good session. And I
Absolutely.
wish again all of you a happy Deepavali and best wishes for your coming days. Thank you. Thank
Wishing
you.
you the same, sir. Thank you. Thank you.